Hello again. Now we've seen typical CNN layers. So we've seen the convolutional layer so far. Now we're going to see the nonlinearity layer. Okay, so these are the layers again. And if you remember, so we had a convolutional layer, nonlinearity layer, pooling layer, normalization layer, and then another layer of the same kind. And some of the, so normalization, for example, we're going to see it later, is optional. So if, just a reminder, so we had an RGB image that we convolved with a filter, because it has 3 channels, R, G, and B, red, green, and blue. So we needed 3 filters corresponding to each channel. And then we did the convolution. And again, this is the convolution, the operation of the convolution, the pink with the red, convolved with the red, plus the green, light green with the dark green filter, and then the light blue section of the image or portion of the image convolved with the dark blue of the filter. And then we add them up, we get this thing 2 here. And we slide the window or the filter, and then we do the convolution again to get the next value or output value here as a result of the convolution. Now we're going to take these values here and apply nonlinearities. So convolutional and fully connected layers being, for example, the multi-layer perceptron, are followed by a nonlinear activation function, a nonlinear activation function. So for example, for a fully connected network, you have the activation, which is the sum of the weight multiplied by the input plus the bias. That's the net activation that you feed to an activation function. So the same thing here. In this case, we feed these values, the results of the convolution, to the activation function. And the activation function that we use its input is a real valued, and the output lies in a small range. For example, 0, 1 for a unipolar activation function, or between -1 and 1 for a bipolar activation function. And then we need this activation function, or this nonlinear function, because we want to learn nonlinear mapping. And if we don't have, in the absence of these nonlinear functions or nonlinearities, we were going to end up with a stacked network of weight layers, and it's only going to give us a linear mapping. And we want this activation function to be differentiable for learning. Remember, when we do backpropagation, we had to multiply with the derivative of the activation function. So this activation function has to be differentiable. And as you remember, as we've seen in the case of the multi-layer perceptron, we looked at the sigmoid and the hyperbolic tangent. Now, just to refresh our memory with the sigmoid, the input is a real number. So this would be the activation. So this should be Z or X, which corresponds to the activation sum of the weights multiplied by the inputs plus the bias. So you feed it to this activation function. And the output for a sigmoid would be between 0 and 1, okay? The derivative, this is the red, is the derivative, looks like this. And it is between, and the maximum value of this, you can prove it by taking this, the derivative of this function. you find the shape, and then the maximum value is 0.25, which is important, as we're going to see here, because it's going to put limitations to the sigmoid function. Another function is the hyperbolic tangent. Again, the input is any real number, is the activation, or again, this value here that we get as a result, in the case of the CNN, as a result of the convolution. And the formula is given by this, just the hyperbolic tangent. And this is the derivative of the activation function of this hyperbolic tangent. And the value, the maximum value is +1. Now, issues with the sigmoid, as we've seen, this is how it looks. And this is the derivative. And if you remember, when we, with the our update learning rule, or the way we update the weights. So then we said that the new weight is equal to the old weight times the learning rate times multiplied by the derivative of the error with respect to the weight, okay? And this is, we're going to see later that we call it the loss. But in any case, when we multiply this and we use the chain rule, we're going to end up with a factor which is the derivative of the activation function, which is this here. And then, so this is our delta W. So the delta W, for example, would be, if this is the value of the activation function, so the maximum that we're going to get is 0.25. And then this delta W is going to be very small. So we're going to have, with the sigmoid function, we're going to end up with a very slow learning. And also, because we backpropagate this, this error, right? The delta. So we backpropagate the delta. So every time we do it, because we have a number of layers. So that 0.25 makes the delta very small. And then we end up having these layers learn okay. But then because the delta vanishes or disappears or gets smaller and smaller, so these earlier layers won't have the chance to learn or to adapt their weights. So this is what is called the vanishing gradient problem, okay? So that's a problem with the sigmoid. Now in response to that, a more popular activation function called the rectifier linear unit, or ReLU, which is a simple activation function, as we're going to see, because it accepts values between, it accepts any values, any real values, and the output is either 0 or this value, or we're going to explain now. So if it's given by the max of 0 or x. So if your x is negative, so the maximum is going to be 0. So the ReLU value function is going to be 0. And then if your x is positive, the maximum of 0 and that positive number is going to be that positive number. So this is nothing else than if, for example, your x or your activation is equal to 2.5, so the corresponding output of the activation function is going to be 2.5. The same thing. If the input to the activation function is 5, the output is going to be 5, and so on. So this is how this is the explanation. So because it takes values either 0 or x, then it is quick to compute. It is the most popular activation function for deep networks, for convnets, for example. And it avoids the vanishing gradient problem and makes the learning faster, because the reason why is because the derivative of this function, it's either 0 for negative values or 1 for positive values. It's not defined for 0, so you don't have that. So if if you go back, just like in this case, if you want to update the rules, or maybe we have this here, if we want to update the weights, then we're going to have, we're going to have either 0 or 1. And then if it's 1, then that delta is going to be, is not going to be faced or affected by the vanishing gradient as opposed. So its maximum is 1. It's not like the sigmoid, which is 0.5, okay? So this is good. The value is good, but it also has problems in the sense that because the output of the activation function is 0 or 1, or the derivative, so the delta W can be, sometimes can be 0, okay? So in that case, if the output of the activation function, derivative of the activation function is 0, the delta W is going to be 0. And we're going to have here no change. This term here would be 0, and we will not be able to adapt our weights or change them. So the new weight is going to be equal to the old weight. So we won't have any learning. We're going to end up with dead neurons when we do the back propagation. Thank you.